Good morning students. In today's session, we will discuss about ideal and non-ideal solutions. Liquid solutions can be classified into ideal and non-ideal solutions on the basis of Rawls law. First, let's discuss about ideal solutions. Solutions which obey Rawls law over the entire range of concentration are known as ideal solutions. Ideal solutions have two important properties. First property, the enthalpy of mixing of the pure components to form a solution is 0. That is, delta H mixing is equal to 0. Here you should understand one thing. A solution is obtained by the combination of a solute with a solvent. When a solute is mixed with a solvent, there will be either liberation of heat energy or absorption of heat energy. In the case of an ideal solution, there is no heat energy is absorbed nor liberated during this reaction. As a result, the enthalpy of mixing is equal to 0. Next, coming to volume. The volume of mixing of pure components is equal to 0. Here we are taking component A and another component B. Let component A be the solute and component B be the solvent. When A is mixed with B, let's say 5 ml of A is mixed with 5 ml of B. When these two components are mixed, we get a solution. The resulting solution will be 5 plus 5, that is equal to 10 ml. That is, after mixing, the total volume of the solution will be equal to 10 ml. It will not be less nor it will be more. That is, it will not be 9.9 ml nor it will be 10.1 ml. So such a solution is called an ideal solution. So thus, for an ideal solution, we have two important properties. One is delta H mixing is equal to 0. Second property, delta V mixing, that is, there is no change in the volume during mixing, there is delta V mixing is equal to 0. Next, we will see the intermolecular interactions. In pure component, the intermolecular interactions will be of the type AA and BB. So I have told you, for a solution, we have a solute and a solvent. Let the solute be A and solvent be B. So they are called the pure components. Before mixing, we call A and B as the pure components. Now, in pure components, the intermolecular interaction will be of the type AA. That is, in component A, the interaction between the component interaction in component A is AA interaction at molecular level. Likewise, in component B, the interaction between the molecules it can be denoted as BB. Now, in a binary solution, due to the addition of the two components, in addition to the above two interactions, there is a third type of interaction, that is AB type of interaction. That is, when component A is mixed with component B, you will get a binary solution. Binary solution means it is a solution which consists of two components. That is, when component A is mixed with component B, you get a solution, binary solution. Now, when A is mixed with B, in addition to AA and BB type of interaction, we have a third type of interaction, that is AB type of interaction. Now, if the intermolecular attractive force between AA, BB are nearly equal to that between AB, then it leads to the formation of an ideal solution. That is, see, if the intermolecular interaction between AA and BB, it's almost similar to AB interaction, intermolecular force of attraction between AB, then we can say that the solution is an ideal solution. Okay, now examples for ideal solution are solution of normal heptane and normal hexane, that is N-hexane and N-heptane, that is one example. Second example is bromoethane and chloroethane. And the third example is benzene and toluene. So ideal solutions are very rare, but still we have some examples for ideal solutions. These are the three important examples for ideal solution. Okay. Next, we will see the graphical representation of an ideal solution. Already you have seen this graphical representation in the previous session. That is, graphical representation is this. You have vapor pressure along the y-axis and mole fraction along the x-axis. In this graphical representation, we have three important lines. Okay, here we have P1 versus Chi1 and the P1 versus Chi1, and then P2 versus Chi2. Then we have that is the total vapor pressure, that is P total. We have three important lines in the plot of mole fraction versus vapor pressure. Okay, so this is the plot. I am not explaining it because already I have explained this graph. Next we will move on to, so this is all about ideal solutions. Okay, now next we will move on to non-ideal solutions. So an ideal solution is a solution which obeys Rolle's law. Non-ideal solution will be exactly opposite to the ideal solution. Solutions which does not obey Rolle's law over the entire range of concentration, they are known as non-ideal solutions. There are non-ideal solution exhibits two types of deviation. They are, one is positive deviation and the other one is negative deviation. First, let's see what is positive deviation in non-ideal solutions. If the vapor pressure of the solution is higher than predicted by Rolle's law, then the solution exhibits positive deviation. Now, what are the reasons for this positive deviation? In positive deviation from Rolle's law, the A-B interactions are weaker than between AA and BB. Again, come back to our solution. We have two components, component A and component B. In the pure component A, we have only AA type of interaction. In pure component B, we have BB type of interaction. Now, we are going to mix A with B. When we mix component A with B, we have a third type of interaction we already studied, that is AB type of interaction in addition to AA and BB. Now, in the case of positive deviation from Rolle's law, AB interaction, that is the third interaction, that is AB interaction, they are weaker than those of AA and BB. Okay. Now, the intermolecular, so we can say that the intermolecular attractive force between the solute and the solvent, that is A is the solute and B is the solvent. So, the intermolecular attractive force between the solute and the solvent is weak than those between solute-solute and solvent-solvent molecules. That is AA means solute-solute, BB means solvent-solvent. Okay. So, AB interaction is weaker, solute-solvent interaction is weak. Next, as a result, since AB interaction is weaker, the molecules of A or B, it can easily escape into the vapor phase because the AB interaction is weak. So immediately the molecule of molecules of either component A or component B, it can easily escape into the vapor phase than in the pure state. So as a result, the vapor pressure of the solution increases and it results in positive deviation. Okay, so since more and more molecules of component A or B, it escapes into the vapor phase, the vapor pressure is increasing. As a result, the solution will exhibit positive deviation from Rolle's law, or the vapor pressure of that solution will be higher than that predicted by Rolle's law. Now, examples for positive deviation: mixtures of ethanol and acetone. Ethanol, you know the formula of ethanol, it is C2H5OH and acetone is CH3COCH3. So ethanol, you should understand, in ethanol molecule, pure ethanol molecule if you take, there is very strong intermolecular hydrogen bonding. Likewise is acetone. In acetone also there is very strong intermolecular hydrogen bonding is there. Now, when ethanol is mixed with acetone, a new bond is formed between ethanol and acetone. And the newly formed bond between ethanol and acetone, it is a very weak bond. As a result, see, either ethanol molecule or acetone molecule, it will easily escape, it can easily escape into the vapor phase. As a result, the vapor pressure of this mixture will be higher than predicted by Rolle's law, and as a result, this mixture exhibits positive deviation. So examples are very important. The first example for positive deviation is ethanol and acetone. Second example is carbon disulfide and acetone. In carbon disulfide and acetone mixture, in that mixture also, the bond between carbon disulfide and acetone is weak, and as a result, the molecules can easily escape into the vapor phase, and as a result, it will exhibit positive deviation from Rolle's law. So this is the positive deviation. Next, we will see the graphical representation for positive deviation. So first you should be knowing how to draw a graph for an ideal solution. Okay, so in that already we have seen vapor pressure versus mole fraction. See the graph carefully. Vapor pressure is along the y-axis and mole fraction is along the x-axis. And here chi1 is equal to 0 and chi1 is equal to 1. That is, mole fraction of the component 1 is increasing in this direction. And here chi2 is equal to 1 and chi2 is equal to 0. That is, mole fraction of the component 2 is increasing in this direction. In this direction, you can see the mouse pointer. Okay, now the first you can see line, there are three lines, line 1, line 2 and line 3. So first line, it is a plot of P1 versus chi1. In the plot of P1 versus chi1, the expected vapor pressure as per Rolle's law, the expected vapor pressure is shown by the dotted green lines. But actually, because of the positive deviation, vapor pressure is much higher. So you can see that this increase in the vapor pressure is shown by this purple line. Okay, so this is the positive deviation for the plot of P1 versus chi1. Next, we will see the plot of P2 versus chi2. So actually, as per Rolle's law, this dotted lines, the green dotted line shows the expected vapor pressure. But actually, our vapor pressure is much higher than that predicted by Rolle's law, and so this purple line shows the increase in the vapor pressure. So that's about P2 versus chi2. Now finally the total vapor pressure you can see, and the total vapor pressure, the expected total vapor pressure is this one that is shown by the dotted line, and but actually the total vapor pressure is much higher than that predicted by Rolle's law, and that is indicated by this purple line. So this is the graphical representation for positive deviation from Rolle's law. Next we will move on to the second type of deviation, that is called negative deviation. Now, first you should understand what is negative deviation. Now, it is exactly opposite of positive deviation. If the vapor pressure of the solution is lower than that predicted by Rolle's law, then the solution will exhibit negative deviation. Now, the causes for negative deviation. In negative deviation from Rolle's law, AA and BB interactions, A to A and B to B interactions, are weaker than those between AB interaction. That is, see, in negative deviation from Rolle's law, component A and component B is there. In component A to A interaction is there, and in component B, pure component B, B to B interaction is there. The AA and BB interactions are weaker than those between AB, that is, after mixing in the solution we have AB interaction. So it is AB interaction. In other words, we can say that AB interaction will be much stronger than AA and BB. So as a result, the intermolecular attractive force between the solute and the solvent molecules are much stronger than those between the solute and solvent molecules. So you should understand one thing, in negative deviation, that is, AA and BB interactions are weaker. Whereas AB interaction, the third type of interaction, that is AB interaction, it is very strong. That is, we can say that the solute, if A is the solute and B is the solvent, the solute-solvent interaction or solute-solvent molecule interaction, it is much stronger than solute-solute and solvent-solvent molecule. So the molecules of A or B can, since the intermolecular interaction between A and B is much stronger, the molecules of component A or B, it is much strong. So it cannot, that bond is very strong, AB bond is very strong. So the molecule of A or B cannot easily escape into the vapor phase. Therefore, the vapor pressure of that solution, it decreases and it results in negative deviation. So this is the reason for negative deviation, because AB interaction, the newly formed AB bond, it is much strong. So as a result, the component A or B cannot escape into the vapor phase, and so the vapor pressure will be lower than predicted by Rolle's law. So that is the reason for negative deviation. Examples: Mixtures of phenol and aniline. In phenol and aniline, the bond between phenol and aniline, it's a very strong bond. As a result, neither phenol nor aniline, it will escape. It has a greater tendency to escape. It does not have much greater tendency to escape into the vapor phase. As a result, the vapor pressure will be lower, and so it exhibits negative deviation. Likewise is acetone and chloroform. In acetone and chloroform, see, there is a very strong intermolecular hydrogen bonding between the oxygen atom of acetone and the hydrogen atom of chloroform. Chloroform is CHCl3, the formula of chloroform. So there is a very strong intermolecular hydrogen bonding between acetone and chloroform, and as a result, neither acetone nor chloroform, it has the tendency to escape into the vapor phase, and so the vapor pressure will be much lower than predicted by Rolle's law. Next, we will see the graphical representation for negative deviation. So always, whether it is positive deviation or negative deviation, first you should draw the graph for an ideal solution. So you already know vapor pressure along the y-axis and mole fraction along the x-axis. We will have three plots, P1 versus Chi1 and P2 versus Chi2. This is the line for P2 versus Chi2, and this is the total pressure. So you can see each line, you can see actually in P1 versus Chi1 graph, you can see the expected vapor pressure is shown by the dotted lines, but actually our vapor pressure is much negative deviation it is. So our vapor pressure is much lesser than that is predicted by Rolle's law. Okay, likewise you see line 2, P2 versus Chi2 graph. This is the expected, the dotted line shows the expected vapor pressure, but our vapor pressure is much lower than predicted by Rolle's law. And finally the total vapor pressure, you can see this is the third line. In this also the expected value of vapor pressure is shown by the dotted lines, but actually the vapor pressure is much less than that is predicted by Rolle's law. So this is the graphical representation for negative deviation. Next, we move on to the other topic that is called azeotropes. Okay, what are well, let's see what are azeotropes. Binary mixtures having the same composition in the liquid and vapor phase and boil at constant temperature are called azeotropes. So in an azeotrope is a binary mixture. Okay, binary mixture means it consists of two components and they have the same composition in the liquid phase as well as in the vapor phase. And also one more peculiarity is there, they boil at constant temperature. Such a binary mixture, we can call them as azeotropes. There are two types of azeotropes. One is called minimum boiling azeotrope and the other one is maximum boiling azeotrope. Now first, let's see what is a minimum boiling azeotrope. The solutions which show large positive deviation from Rolle's law, they form minimum boiling azeotrope at a specific composition. Example for minimum boiling azeotrope is ethanol water mixture. Second type of azeotrope is maximum boiling azeotrope. Now, in maximum boiling azeotrope, the solution which show large negative deviation from Rolle's law, they form maximum boiling azeotrope at a specific composition. Example, nitric acid water mixture. So these are the two types of azeotropes. One is minimum boiling and the other one is maximum boiling. So please study the examples for minimum and maximum boiling azeotropes. Then one more peculiarity is there for azeotropes. Once a solution attains this azeotropic composition, the liquid and the vapor phase will have the same composition. Okay, so once a solution attains this azeotropic composition, the liquid phase and the vapor phase will have the same composition and no further separation occurs. That is, we cannot separate the components. So that is the peculiarity of this azeotropic composition. Okay, so that's all about azeotropes. I hope you have understood this session.